Okay, this is part 7 of our introduction to pseudospectral methods. In the previous part, we discussed Chebyshev interpolation, and here we'll look at how to take derivatives of these transforms. So a derivative of u with respect to x is going to be represented by, it's its own function of x, and so we can represent it by this Chebyshev series here, where Cn prime just indicates the coefficients that correspond to the derivative function. We can evaluate these coefficients using a recurrence relation, and Boyd, in his book Chebyshev and Fourier Spectral Methods, the second edition, page 298, gives this recurrence relation that I've changed the notation for slightly. So we start at the high n and then we go towards 0. So Cn prime is 0, Cn minus 1 prime is 0. This one isn't part of the series, but we can, so that's why it's in parentheses. But and then the next one, n minus 2, and so forth down to 0 are given by this simple recurrence relation. So you can just plug these numbers in. Here gamma is just a constant that is different for different values of n, so gamma 0 is 1/2, and for other values it's 1. There's a function that computes these coefficients for us. NumPy.polynomial.Chebyshev has the function chebdir, and it returns the size n minus 1 array C prime given C. So you just call chebdir with your given with the coefficients of the U field, and it will compute the C prime coefficients. Now its size is n minus 1. And so if you want the full size, then you just have to append a 0 onto that array. So here's an example of using that recurrence relation. So for n is 5 points, we'll just create an arbitrary array of C's, and then the C prime will initialize and then just loop through applying that recurrence relation. And here we don't formally create the gamma array, it's just ones except for the last, or the 0th element, and so we just apply that 0th element here, times equals 0.5. We output that, and then we compare it against the chebdir function, where we append the 0 to the last value, and you can see that the two arrays are identical. So that's how you can calculate these, the derivative of the Chebyshev series. Okay, so let's look at an example of doing that. So we'll compute the derivative of the Runge function again, and then for variety we'll compute the derivative of this other function, 0.1 e to the minus 2x sine of 6x minus 8x. That's this one down here. So we have 17 points. We'll use n as 17. And then we'll use the roots grid, so Cheb points 1, and then we have u is just you Runge, the Runge function at these grid points, and then we calculate the P array here, and so the C is this, so that we can use the discrete cosine transform like we discussed in the previous presentation. So we have the discrete cosine transform of u, that gives us A, and then we convert it to C by multiplying by P and dividing by N. So we can go back up here, that's applying this. So we need to get the C's, so we do that by given the u, we take the discrete cosine transform, that gives us A, then multiply A by P and divide by N, and that gives us the C. Where again, the P is given by 1/2 for the first element, and all the other ones are 1. Okay, so now we have the C. Then we can take the Chebyshev of C and append 0 to it, and then we can interpolate the function everywhere. So on the big grid of all x values that we defined in the previous presentation in the boilerplate. There's a slide up here with the boilerplate xx and our range function. Okay, so it's as easy as that. So again, create the grid, find the C coefficients, find the C prime coefficients, and then we can interpolate it wherever we want. You can see that it doesn't do that impressive a job with 17 points on the range function. This other function that we try, it's nearly perfect. So you can play around with the number of points, and you can see how these behave. Okay, I'll just note that this Chebyshev function doesn't really care what your grid is. It only operates on the C coefficients, so it doesn't really matter whether you're on the roots grid or the extrema grid. So we could have done this on the extrema grid by just changing this to 2, Cheb points 2, and then when we do the discrete cosine transform, we'd need to go type equals 1. Then once we have C, the Chebyshev is the same as it is here, and also this Chebyshev only operates on the coefficients, so it's the same as it is here. Okay, let's look at derivatives on the grid in a little bit more detail here. So on the roots grid, let's denote C prime as this script D as a function of C. And so basically the script D is the same thing as this Chebyshev and appending 0 right there. And so if we want the derivative with respect to x, then we need C, and C is the discrete cosine transform. So we do the discrete cosine transform of u, then we multiply that by this p, and then this would then also be divided by n, and that gives us C, little c, coefficients. And then we take the derivative of that to get the C primes, and then we need to take the inverse transform, so we need to convert those C primes back to effectively A primes. So there would be an n here and a divide by these p's here, and we take the inverse transform to get back to u. And we've canceled the n's because they appear in the numerator and denominator, and that's consistent with what we described before, where we've got these n's right here. Okay, so this is similar to what we did for the Fourier pseudospectral method, where we had a discrete Fourier transform, and then we multiplied it by a constant, and then we did an inverse discrete Fourier transform. And here we do a discrete cosine transform, and we scale it. Then rather than multiplying by a constant, we do the derivative operation, then we unscale it, and then we invert it back, and it gives us the derivatives here. Remember, this is the name of the game for pseudospectral methods applied to PDEs, is how we evaluate derivatives on the grid using these high-order methods. Okay, so that's the roots grid. On the extrema grid, it's the same thing, but we have these p coefficients are a little bit different, and we use a type 1 cosine transform instead of a type 2 transform. And the factor of n-1 and divided by n-1 is canceled in this case. All right, so if we have an nth order derivative, we can just apply the derivative multiply, and that can be done with this Chebyshev function, you just tell it the order of the derivative. So it defaults to n as 1. So up here we just had n as 1 when we did Chebyshev, didn't put anything. If you want a second or third derivative, just put comma 2 or comma 3 to get those. So this isn't like, this D is going to be literally implementing the Chebyshev on the result of this expression. Then you multiply it by this, and then undo it with the inverse. And you'll notice here I just kept the n minus 1s are shown explicitly. Okay, that's for the extrema grid. For the roots grid, we would just replace this n minus 1 with n, which cancels, and this pi just gets replaced with p2, and the ci and c minus 1i with c2. Okay. So let's look at an example. We'll do the 1D heat equation. So we have du dt is alpha, d2u dx squared. Alpha here's a diffusivity, like gamma that we used before. And we're going to have Dirichlet boundary conditions. So, and we'll just make those 0 and 1 on the left and right. Then we'll use a 0 initial condition. And we'll have a source term equals a constant, just 1 here. So the pseudospectral solution can be solved using the method of lines. And we're basically just putting in the equation for the second derivative similar to this. And we're going to be using the extrema grid here. And then the array U already has the appropriate boundary conditions, and as we solve this, we'll just make sure that this rate is 0 for the points on the boundaries, since we don't need to update the known value of U. So here's the code for that. We have the diffusivity here is 1, source term is 1. Our initial condition is 0 everywhere except we set the boundaries to be consistent with our boundary conditions. And then the rates function is effectively our right-hand side here. We're going to evaluate that rates function. And for that, we first take the discrete cosine transform, type 1, because we're on the extrema grid. So the type 1 discrete cosine transform. Then we're going to multiply that by p, and p is 1s everywhere except for the first and last entries of the array are 1/2. So we multiply by 1/2. And then normally we would have a division by n, but that cancels with the multiply by n. So that gives us c. Then we calculate c double prime, and that's we take the second derivative, which is Chebyshev, and then we're going to append the 2 zeros on the end of that, because we took the derivative twice, and we want the array to be the right size so that we can invert it and get all of the correct size back. Okay, so that does the derivative twice, appends the 2 zeros, then we divide by the p here, and then we do this final transform. Oops. This final transform, again type 1, and then the rates are simply the diffusivity multiplied by the second derivative plus the source term, and we set the rates 0 to be 0 on the first and last entries on the boundaries, since we don't need to update the known value of u there. Then we just solve it with ODE-int, and we can plot the results, and this is what we get. So you can see the evolution in time. We start with zeros except on the boundary, which is 0 and 1, and then we watch the evolution in time. We have a source term here, and that results in this steady state value. So at steady state, the divergence, divergence of the flux, the heat flux, is balanced by the source term, and we get an equilibrium solution here. Okay, great. So pretty straightforward. Not a lot of code here, and when we're making use of the functions that are available. So let's look at how to deal with a Neumann boundary condition. In this case, instead of specifying the value of u at the boundaries, we're going to let the boundary at x equal 1, we're going to specify its slope, u prime, instead of its value. So here we have u prime is beta, where beta is some slope that we choose. We'll use a linear initial condition that satisfies the boundary conditions. It's good form to make your initial conditions satisfy the known boundary conditions. And we'll rewrite the PDE as shown here. So we're going to split this second derivative into a derivative and a second derivative. And we do that so that we can so that we're explicitly dealing with the derivative, so that we can impose the Neumann boundary condition. The inner derivative is given just like we had, so the cosine transform, scale it, take the derivative, unscale it, take the inverse, and that gives us the array of derivatives, first derivatives. Then we can impose the Neumann boundary condition at the upper boundary, since we know it. We can say, okay, let u prime at the end of the domain equal beta, and then we can apply a derivative operation to u prime to get the second derivative. Then we multiply by alpha, add the source term, and that constitutes our rates, which we can then advance using the method of lines. So that's indicated down here, where we've done the evaluation of that first derivative that has the Neumann boundary condition in it, and then take the final advancement, or the final form that we can then advance. So here's the implementation of that. So I'm letting I'm letting that Neumann boundary condition be 1 at x is 1. And then we first compute u prime, so a discrete cosine transform, scale it, take the derivative and apply of the Fourier, or of the Chebyshev coefficients, append 0 to those, then we unscale it, convert it back using the inverse cosine transform, then we apply our Neumann boundary condition at x equals 1, and this looks funny because I inverted my x grid, so x is 0 when x is 1.0. That's my first point of the array because we went backwards. And then we do the second derivative. Looks really similar to what we did for the first derivative. So the discrete cosine transform, scale it, take the derivative, append 0, and then unscale it, take the inverse transform, and then finally we go multiply by the diffusivity, add the source term. And then we don't need to change the Dirichlet boundary condition at x equals minus 1, but we do allow the boundary condition to be updated at x equals 1 because we're advancing that. So unlike the Dirichlet at both ends, where we set the advancement of u to be 0 at both ends since we know u at both ends, here we only know u at one end, so we're only forcing the rate to be 0 at the Dirichlet end. Okay, and then if we look at the solution there, our initial condition is a straight line that satisfies the Dirichlet boundary and the Neumann slope of 1.0. And then with the source term on it, we increase our temperature field if we're solving the heat equation. But notice that the slope is always 1.0. So all of these lines are parallel at the right side, consistent with that Dirichlet boundary condition. So not very difficult to implement, but you have to be careful about exactly how you do it. And importantly, it's more expensive to do this because we end up having to take discrete cosine transform inverse 1, 2, 3, 4 times whereas for the Dirichlet boundary conditions, we only had to do it twice. And the reason for this is that these are global functions, and so to maintain the high order, we need to impose the Dirichlet boundary condition, the Neumann boundary condition, appropriately so that it applies across to all the modes when we do the transforms. Okay, now Robin boundary conditions, those are mixed conditions where you have both a Dirichlet condition and a Neumann condition. So you can write something like this. And in that case, you basically do exactly the same thing as you would for the Neumann condition. So for the Neumann condition, we imposed the slope equals beta at the boundary. For Robin, since we know u at the boundary at any given time, it's really easy to impose a boundary condition that looks like this, since we can take the known u, multiply it by the given gamma, and then add beta to impose the slope, just like we imposed just beta when we had the Neumann condition. So nothing special. You treat Robin basically the same, and you just use the known u at the given time when you're evaluating that that Robin boundary condition. Okay, and we'll stop there. And in the next presentation, we'll extend this to two-dimensional problems.